The perturbative treatment of any interactions of the fermions will basically follow the same lines as the treatment we had in the scalar field case. So one of the main ingredients is the two-point function defined as this time-ordered product. So let me just use the psi bar, since psi bar will appear in most of the computations rather than psi dagger. And keep in mind that psi and psi bar, they are just four component spinors or row or column and row matrices. Let's look at the K and L components. Now, of course, the fact that the fermionic fields have anti-commutation relations will lead us to some differences. One important difference is the definition of this time-ordered product. For the scalar fields, the time-ordered product was defined as whichever operator has a later time, it acts later. First, the earlier operator acts, then the later operator acts. So if the chronological order is different, then we just change the position of the operators. So what time ordering tells us is that we should, before using that expression, we should just change the order of the operators, setting the commutation relations to 0, such that when we just commute the operators, at the end all the operators should appear in chronological order, like here. Now, in the case of the fermions, though, let's just take two fermionic fields. They can be x and y, psi1 and psi2. They can be any component of the Dirac field or the conjugate field, etc. It doesn't really matter. And this is defined as, again, just similar to the scalar case, but this time the time ordering operator tells us that we should change the order of the operators, this time using anti-commutation relations and setting the anti-commutation to 0 within the time ordering operator. Well, that basically tells us that whenever we change the position of the operators, we get a minus sign. So this is equal to psi1 of x, psi2 of y, if x0 is later than y0, and it is minus psi2 of y, psi1 of x, if y0 is later than x0. And hence, even within the time ordering, if you change the position of fermionic fields, you introduce a minus sign in your time ordering. Now let's go to the two-point function that we would like to calculate. So this is equal to, well, we will have two momentum integrals. Let's call them P1 and P2. 2 pi cubed square root of 2e P1 d cubed P2 divided by 2 pi cubed square root of 2e P2. Now, if x0 is later than y0, we have the matrix element of first the psi and then the psi bar. Well, psi k is a p1, a u with the momentum p1, but now we are taking the k component of u, and then we have e to the power minus I p1 x plus b p1 dagger v k, the k component p1 e to the power I p1 of x. And then we have the psi bar. Psi bar will be a dagger p2 u, we are taking the L component u bar of p2 e to the power I p2 of x plus b p2 v of L, v bar of the L component of V bar, P2, e to power minus I P2 of x. In the other case, if y0 is larger than x0, then we have these two terms, they have to change their position. So let me first write this one. Then the other one. Now we can do some simplifications already. You see B acting on vacuum will just give us 0. So this doesn't contribute. And B dagger acting on the bra, the vacuum bra, it will also give us 0. So you see, if x0 is later than y0, we have a particle. So that is the particle created by A propagating from, let's say, no, sorry, this is y, from y to x. This is y. Now, in this case, if y0 is later than x0, then this acting on the this operator acting on the vacuum will give me 0. And this also will give me 0 acting on this vacuum over here. So in this case, it's the particle, antiparticle that is propagating from x to y. Here it is the particle that is propagating from y to x. So let me rewrite the simplified expression. d cube p1 divided by 2 pi cube 2e1 ep1 square root d cube p2 divided by 2 pi cube square root of 2e p2 theta x0 minus y0. Well, I have these two terms, so that they give us e to power minus I p1 of x plus I p2 of y. Vacuum A of p1, A of p2 dagger. Vacuum u of k p1, u bar of L p2. And for the other case, theta y0 minus x0, I only have these two terms, e to the power I p1 of x minus I p2 of y, vacuum b of p2, b dagger of p1, v bar of L p2, v of k p1. So now let's look at these matrix elements. So let me start with the first one, A of P1, A of P2 dagger, vacuum. This is equal to A of P1, A of P2 dagger, plus A of P2 dagger, A of P1, vacuum. Basically because A of P1 acting on the vacuum gives me 0, so I just added 0, but now it became the anti-commutator of A of P1 and a dagger of P2. But that anti-commutator over here is just 2 pi cubed Dirac delta cubed of P1 minus P2. And vacuum is normalized to 1, so this is 2 pi cubed Dirac delta cube P1 minus P2. Well, we do the same treatment for the other matrix element. This will also be 2 pi cubed Dirac delta cubed of P1 minus P2. So let's substitute these matrix elements into our previous expression over here. So we have d cubed P1 divided by 2 pi cubed square root of 2e1, d cubed P2 divided by 2 pi cubed square root of 2e2, and then we have step function of x0 minus y0 e to power minus I p1 of x plus I p2 of y, and 2 pi cube Dirac delta of P1 minus P2, and I also have this product. And then I have the other case. No, okay, so let me also make one correction here. You see that in the time ordering there is a minus sign when the fields are exchanged. So this is actually a minus sign. y0 minus x0 e to the power I p1 of x minus I p2 of y, 2 pi cube Dirac delta cube p1 minus p2 of this one. Now I can evaluate the P2 integral. Now when I evaluate the P2 integral, these Dirac deltas just tell me that P1 should be, the three component P1 and P2, they should be equal, but that means the energies will also be equal. So now these 2 pi cubes also cancel. So I will end up having d cubed P divided by 2 pi cube square root of 2e of, no square root anymore, 2EP step function x0 minus y0 e to power minus I p x minus y u k of p1 u l bar of p2 minus step function of y0 minus x0 e to power I p x minus y, and vk of p1 vl of p2. Let me check the indices over here to make sure that they are correct. So I see here v bar of l of p2, vk of p1. Yes, the indices are correct. Now to proceed with our computation, we still need to calculate these these are P1. Everything is P now. Now to proceed with the computation, I need these expressions, these matrix elements. Well, let's just go ahead and calculate those matrix elements. You see this U of k, and keep in mind that I still have a summation over the spins. U of k, U L bar of P, is actually the U of P, U bar of P. Note that now this time these are the, I take the k element of U and L element of U bar, so this is just a number, but here I multiply the column matrix U with the row matrix U bar. So this whole expression is a 4 by 4 matrix, and I'm just taking the KL component of this 4 by 4 matrix. So I know what U and U bar are. So this is equal to sum over the S. U is given by square root of sigma P, square root of sigma bar P. U bar is U dagger. Now this is psi S, psi S. U bar is psi S dagger, square root of sigma P, psi S dagger, square root of sigma bar P. Gamma 0 is 0, 1, 1, 0. I repeat, this 1 is a 2 by 2 matrix. So let me just multiply these two first. Sigma P psi S, sigma bar P psi S, and psi S dagger, square root of sigma bar P, psi S dagger, square root of sigma P. So basically multiplying with gamma 0 over here just exchanges these two elements. And at the end I will take the KL element of this matrix product. Now this is equal to square root of sigma P, psi S dagger, summed over S, square root of sigma bar P. But note that psi 1 dagger is 1 0 1 0. This is just the matrix 1 0 0 0. Similarly, psi 2 dagger is 0 0 0 1. So if I psi sum over S psi S dagger is 1 0 0 0 plus 0 0 0 1, which is nothing but the identity matrix. So this whole thing over here is the identity this thing is identity matrix. So I can actually just erase it, and I will have a somewhat shorter expression. Okay, let's continue. This element is sigma P squared, so it's just sigma P. Here we get the sigma bar P, and here I get the sigma bar P, sigma P. But this matrix element and this matrix element is just M. So because sigma P, sigma bar P, when you multiply them you get M squared, you take the square root, that's just M. So this is M, sigma P, sigma bar P, M, the KL element. So at the end of the day, when I calculate this, this is equal to M sigma P, sigma bar P, KL element. But you see, this is nothing but M times the identity matrix plus P mu gamma mu, or P slash the KL element. So let me just remove the indices also. Okay, so at least we have another matrix identity for these spinors. Now we need to do the same thing for the other matrix element. You see here we have calculated this one. This is a P slash plus M, the KL element. Let's calculate this one also. And there is also a summation over the S. So this will be equal to sum over S. V is square root of sigma p psi minus square root of sigma bar p psi, and V bar is minus square root of sigma bar p psi dagger first, and then psi dagger sigma p, which will give us, again I will just use the fact that psi dagger, these are the S, summed over S gives us the identity, so this becomes minus square root of sigma p sigma bar p, and sigma p minus square root of sigma bar p sigma p, which is with this time with a this is just, well, let me write it out explicitly. This is minus m. Okay, this matrix element is this multiplied with this one. Okay, sigma p, this is sigma bar p, sigma bar p. This is just p slash minus m. Again, the KL element. So let me make sure that I have the correct signs everywhere. So whenever I get the dagger and multiply by the gamma 0, these two are exchanged in this row. So when I multiply, okay, there is a minus sign over here, there is another minus sign over here, and no minus signs over here. Okay. So this is what we have, p slash minus m. Now we can use this in our earlier expression. So we were calculating this one. Now I know that this whole thing is p slash plus m KL element, and this whole thing is, let me take the minus out, m minus p slash KL element. So these minus signs, they cancel. Now to continue with the computation, I will try to simplify this expression slightly. So first, in the second term, let me just set p goes to minus p. Now the reason why I set p go to minus p in the second term is so that the exponentials will look similar. So if I do that, then I get d cubed p divided by 2 pi cube, 2e of p. I have e to the power I p x minus y, because now this term is the same in both terms. Inside I have theta of x0 minus y0 is there minus I e of p x0 minus y0 p slash plus m plus theta y0 minus x0 e to the power I e of p x0 minus y0 m minus, let me rewrite this also as m plus gamma 0 e0 minus gamma dot p, and here now I have m minus gamma 0 e0 plus or minus, sorry. You see this p slash has gamma 0 e0 minus gamma dot p, but remember in the second term I make this replacement, so this sign becomes minus. So the first term and the second term, they actually differ by only the sign of e of p. But if you remember what we had done in the case of the scalar fields, we can just reorganize, write this, including these step functions, we can write them as a time ordered product, as an integral, as a complex integral. And from that complex, including this e of p, and from that complex integral we would obtain dp0 divided by 2 pi, a factor of I, p slash plus m divided by p squared minus m squared plus I epsilon e to the power minus I p x minus y. But remember here p is actually p0, p is just p0 and p0 is not actually equal to e of p. We are just integrating over it, and hence we get the propagator d4p divided by 2 pi to the 4. Well, in this case the I is in the top, I of e to the power minus I p of x minus y, I p slash plus m divided by p squared minus m squared plus I epsilon. So if you compare this with the propagator we had for the scalar case, well, essentially it's just this part is the extra part. So that is kind of the end of the computation of this two-particle, two-point function. And of course we are looking at the KL element of this matrix over here.